right, good morning. So today I will talk about how we can analyze large amounts of data in Python. And we're going to use a package called Pandas, and that will cover most of the parts of the lecture. But before I start, I want to clarify some questions that we had from last time. And there was one moment where I wasn't quite sure what was happening. If you remember, we had this string, mo, ha 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 ha, and then ha he. And I was trying out this regular expression where I had a essentially what I wanted to do is I wanted to grab the first two characters and the last two characters and swap them and remove all the parts in the middle. So removing all these ha-has and only end up with he, H-E-M-O at the end. So my idea was to create a group that consists of some word characters, and I tried to make this non-greedy, so I added the question mark afterwards. And so that first group was supposed to grab the MO, the first two. Then I thought, okay, so what I will then do is I create another group that consists of loads of HAs, and at the end, a final group where, again, consisting of word characters that consisted of the HE. And so the key part here was that I used this question mark symbol here to make these \W star is normally greedy. So it tries to match any word character, and it tries to match as many word characters as possible. But by adding the question mark, I make it a non-greedy operator. So it's trying to match as few characters as possible. Okay. So you can see the difference very clearly if I remove this the question mark. Now here on the right-hand side, you can see well, in this case, I have four groups here. And group one is the first part here. Is this first part here. And now, at the moment, group one matches the entire string. And that's because the entire string consists of word characters, and the regular expression just tries to match as many as possible. Now, if I add a question mark here, it makes it a non-greedy operator, and so it's trying to match as few word characters as possible. But of course, then the result is that it just doesn't match any word characters at all. So group one is completely empty. And then afterwards, we are expecting at least 0 or more character groups HA. But because we are still at position 1 in the string, there is no HA. So the regular expression says, well, there's group 2 is also just the empty string. And then at the end, I'm again trying to match word characters, but again as few as possible. So again, I end up with an empty string. So this is clearly not what I wanted to do. So the first thing that I thought of is, well, first of all, we want to match the entire string. So what I should do is I should add the begin of string marker and the end of string marker here. So now what happens is that, so something has changed. So the last group now consists of the entire string. So why is that? Again, the first group tries to match as few characters as possible, still ends up with not matching anything, just stopping here. The second group tries to match HA characters, but because we're still at position 1, there is no HA character at the position 1, so it just doesn't match anything. And then the last group tries to match word characters as few as possible, but we have to reach the end of the string. So then the last group just matches the entire string. Okay? So that's again not quite what we want. So then one option would be to say, well, maybe we know that these two first consist of exactly 2 word characters. So then what I could do is I could say, I use this quantifier and say I'm looking for exactly 2 characters at the beginning, followed by HAs, followed by some more word characters. And so now indeed the groups work as expected. So we have group 1 is the MO that we're looking for, group 2 and 3, which are the intermediate parts, are all the HAs, and then at the end we have group 4, which is the HE. And so now I could use my substitution field here and say \4\1, and I would get the result HEMO that I was looking for. Now this unfortunately breaks if you start adding more characters here. So now if I have maybe MOMO here, or maybe just MO, then this fails. So if we wanted to make this more robust, one way you could do that is to say the word characters at the beginning, we're not looking for exactly 2 characters, but we're looking for any characters that are not HA. Okay, so we're trying to negate essentially what we're looking for the middle part. We're looking for any characters that are not HA. So how do you do that in regular expressions? Well, first of all, we create a character class, which is these square brackets, and then we invert them. Remember, in the character class, the head symbol was for not. So I'm not looking for a symbol. And so in principle, I could just add any symbol in here. So for instance, M. Now it would just look for any non-M's, but I'm looking actually for the character tuple HA. So I want to look for any characters that are not HA. So what I'm doing is I create a new group. That group matches exactly the word HA. And I can make this a group without numbering. So I add this question mark colon at the end, at the beginning. So now this looks quite complicated, but the first part here essentially matches any characters as long as they're not the word HA. And the second group matches anything that consists of HA repeated as often as possible. And then the last character matches all the rest to the end of the string. And so now we have a robust solution. So now I can add any characters here. Or do we? So here we get HEM, which is expect. Then we have, so that doesn't work.
Maybe it's because you're only taking one. Shouldn't you have a star?
Right, that's right, of course. So of course we can have arbitrarily many, as long as they're not HA. And so now I can add any. Right. Why is this again not working? So, okay, it works here. Okay. Seems to work. But then, of course, if I accidentally had an HA in here, followed by some other stuff, now it's not quite clear which HAs I'm looking for, so it matches the first one, while the second HAs belong to the suffix, so to speak. Okay, so that was that example, hopefully clarified. Any questions regarding regular expressions? No? Okay. So then let's continue with pandas. So today we're making the first steps towards the following assignment, the last assignment, where you're going to work with quite a lot of data. And of course we could store, so what I'm thinking of, and I give you some examples, for instance, if you're analyzing maybe large time series. So this could be financial data, it could be data from sensors that you're acquiring from somewhere. and you're trying to do some analysis. You're trying to extract some information out of this data. And so, of course, we could use the tools that we already know. We could load this. I mean, this data essentially consists of often a sequence of numbers or maybe tables. And we know how we can represent sequence of numbers, right? So they could be Python lists, or they could be NumPy arrays, and we can operate on them. But Pandas simplifies this work. It's essentially a tool built on top of NumPy and the Python data structures that allows us that facilitates the data analysis somewhat. And so, for instance, what Pandas is very good at is if you have multiple data sets and you want to merge them. And I'll give you an example later on where we do that. Then it's often with real data, you often have the problem that you have some missing parts in the data, right? So maybe your sensor failed, and so you just have an entire window where there's nothing. And so you maybe have to fill out that information, and you have to maybe also fix inconsistent formatting that the sensors provided. And then, of course, an important problem is always importing and exporting the data. Maybe you got the data as Excel files, or as just pure text data. So we need convenient ways on how to how to import the data. And then, of course, we want to do some analysis on that. So we need some computation and plotting functionalities, which is also provided in Pandas. So there's some information about the Pandas package. So the official documentation is actually quite good, but there's also a cookbook and an entire book also if you want to look that up. Now, installation is fairly straightforward. If you have Anaconda, it's already part of the Anaconda distribution. And then if you're on a Miniconda, so Miniconda is the small version of Anaconda without any extra dependencies. So there you can use the Conda package installer. So you write Conda install Pandas. Or if you have any other Python distribution, you can pip install pandas -- user. If you're in your virtual environment, for instance, this would install it in your local directory, in your local environment, and otherwise in your user-wide environment. So then let's start. So the first thing, we're going to look in a real example soon. But before we can start, we of course need to import Panda, and the most important imports that you need when you work with data with Pandas is that you import Pandas, and because I'm getting too lazy to type in Pandas all the time, I import it and create the shortcut PD. So whenever you see PD, I'm referring to the Pandas package. And also we'll make use of NumPy, so I also import NumPy as NP. So then the question is, which kind of data can we analyze? And I've collected some of the maybe interesting data sources that you might want to analyze at some point. So quite a nice data source that you can access is from SSB, the Norsk Statistics Sentralbyrå, and they give you loads of databases that you can download. So for instance, if you're interested in employment rates over years, immigration rates, housing market, and so on and so forth, you can download these typically as Excel sheets in comma-separated files, and then you can start doing your own analysis on it. Then, of course, we have Fin. Unfortunately, Fin used to have an open API, but now they're only open up for business. So if you want to create it, but in principle, right? So if you wanted to collaborate with Fin and you wanted to make an extension, then you could use the Fin API to extract information about their market, for instance. So then there's the Hooter API. So that one is actually open, and you can use it. And it gives you, for instance, information about live departure information, any delays and so on. And so I've built, for instance, this little, it's just a Raspberry Pi with a e-ink display that hangs in my kitchen, and it just shows me when the next train station leaves, when the next train leaves. So I don't need to check my phone all the time. So these are really simple things once you have access to this live information. And then you have Uhr for weather information. And so today in this lecture, we will actually use some data about the Oslo bikes. And so we will do some analysis on who uses the Oslo share riding bikes and when are they used. Do we find some patterns in that usage and so on and so forth. So you can get both live usage data and also statistics from the last months. Yeah, and so in this lecture, we will make use of this data. And then, of course, if you're more interested in financial and economic data, there's a webpage called Quantal. And in general, nowadays we are all in this era of smart devices and Internet of Things, and these are all potential data sources that you might want to tap into. Right? So most likely you have at home a smart plug or a smart sensor that shows you the temperature, whatever. And typically you can get access to the underlying sensor data and can start analyzing them yourself. So when we do data analysis with Pandas, we have to know the underlying data structures that Pandas uses. And they're essentially just two. There are two fundamental data sources that we work with all the time. And the first one is called series, so pandas.series. And that is that a Pandas series represents a one-dimensional labeled data. So you can think of it as almost a NumPy vector, but each item in that vector has an index or a name. So to give you an example, so this is how you create a series. You write pd.series, and then in this case I initialize it with a list. So these are the values that I have in my series. And you can see I can use normal integers, and then I also have NaN, which stands for not a number. So this is np.nan, represents a missing value here. And then I have two more values. And so the result is shown below. And what's interesting here is that we have the values here in the second column. And in the first column, we have the indices. And so by default, a time series is just, the values in the time series is just indexed from 0 to 1, 2, 3, and so on. But we can also change these indices. We can explicitly set, maybe we are not, maybe the values are not represented by 1, 0, 1, 2, 3, 4, 5, but maybe by A, B, C, D, E, F. And so what you do then is the initializer is the same, but now we can also provide the index attribute, where we need to provide a list of the same length, but now with the name of the indices. So this is now, and the result, you will see now the indices here in the first column. So this is a bit abstract, but it becomes a lot clearer if we now start working with time series data. So imagine you have a sensor, and then typically what you want is your index becomes the time when the measurement is taken, and then the value is the actual value of the sensor. And so the way you do that is I need to create a index that consists of all the different dates. And so I use the facilitator function pandas.dateRange, where you provide the start day and then just the number of days here, periods equals 6, gives you the number of days into the future. And so dates now is a list starting from the 23rd of October 2018, going to the 24th, 25th, until the 28th. And then I can create a new series now with the values again, but now this time I use the dates as the index, and the result is seen here. So now for each value, as an index, I use the associated date. And so you can clearly see that, I mean, this is how you would store a value of a single sensor in a sense. Okay? So then often we're not only dealing with a single sensor, but we're dealing with many sensors, many data values. And so the second important data structure in Pandas is called data frame. And a data frame is a two-dimensional labeled data structure. So it's essentially a matrix, and each column in the matrix consists now of one series. Okay, so a series was a one-dimensional data column, and our data frame is simply many of these series next to each other. So the way you create a data frame is that you call pandas.dataframe, and then you provide, or you can provide, the entire matrix as a numpy array, for instance. Here I just used random numbers of a random matrix of 6 times 4. And then again, you can use indices. So each data frame also has an index, and I can use the dates here. And I can also give the columns a name. So here I provide a list A, B, C, D. And the result is now a matrix of, with 4 columns and 6 rows. Each row has as index the date, starting from the 23rd of October all the way to the 28th of October. And then the first column is called A, the second column is called B, C, D, and so on. So that's how you create a data frame from when you have the data as a matrix, as a numpy matrix. You can also create a data frame if you have the data as a time series. So if you have 2 time series, one representing a column each, then you can just provide a list where you say the first column is called A, and it uses the time series S1. So remember the time series S1 up at the beginning here. I called them S1, S2, and S3. And so now if I want to create a data frame that consists of 2 of these time series, I can just say A colon S1, and the second colon B should be S2. And this is the result. So the indices of A of S1 was 1 to 5, and the indices of S2 was A to F. It used different indices. And because it uses different indices, it actually appends the data. So the indices is kind of a unique identifier. And when you create a data frame with these 2 series, it creates the indices from 0 to 5 and these indices from A to F. And of course, for 0 to 5, we have values from S1 in column A. So here we see the actual values of S1. But for the time series S2, there was no index 0, so that we don't have any values here. So Pandas automatically uses not a number or missing value here. So missing data is always filled with not a numbers. So, and the same thing also goes the other way around. If you have a data frame and you can use this indexing notation where you specify the name of a column and you specify a specific column, for instance A, what you get is a time series again. Right? So you can create a time series, make it into a data frame, and then you select that column again and you get a time series again. So this is really the kind of the 2 basic data structures that we work with all the time. Now in practice, we don't typically want to type in all the data in a Python list or a NumPy array. In practice, we load it from a file. And so the most convenient way of loading in data is using the read functions. And there's quite a lot of them. If I Let me see. Probably have to. There we go. So here you have all the read functions that you can use. You can see you can read from CSV, which are comma-separated files. You can read from Excel files, HTML files, and so on and so forth. SQL. So there's various different data formats how you can import data. And so specifically, we will use the read CSV file in a second. So now let's start looking into the Oslo bicycle data that we want to analyze. So if you go to the web page, you can see that you can either download live data or you can download statistical data from the past months. And so I decided that it might be interesting to analyze the data from a specific month. And so I chose August to September 2016. So I downloaded the data, and you can see this is what it looks like. These files are called trips 2016.10.1, which is 1st of October, until 2016 31st of October.csv. So that's clearly a comma-separated file for all the trips that happened in October. And then I also downloaded the same thing here for August and then for September. So we have in total 3 different CSV files. And then I can use the bash command head, and that just lists the first few lines of a file. And so we can start inspecting what this file actually looks like. And it's fairly well structured. So in the first line, we have the titles of each column. So we have a start station. And if you look at the first column here, these are kind of numbers, 283, 169, 211. So these really seem to represent some identifiers for a station in Oslo. And then we have the start time. This is the second column here, all the way to here. And this tells us when the bike was taken out from the station, right? So the day and the time. And then we have the end station. That's again a identifier, 238 or 175. So that's again an identifier for a specific station. And then we have the end time, which is shown here. So this tells us when the bike was put back into the station. So since this is a comma-separated file, it's the obvious function to use to import that is the function read CSV. So the way you do that is you call pandas.readCSV, you provide the name of the file, and then there's also this argument separator that specifies how the different columns are being separated. You can execute that. It takes a second, and then we have the results and bike stats. We can check which type it is, and we see that's a data frame. It makes sense that it's a data frame because this is a matrix, right? It's not just a single column, then it would be a series, but it consists of multiple columns, so we get a data frame out. And so then we can actually print it, and this is what it looks like. So we have exactly the data as before, but just now in a nicely formatted in a Pandas data frame. So you have the start station as one column, the start time, the end station, and the end time. And then as index, here the trips are just indexed from 0 all the way to let's see how far we go. So it's some 29, and then it just stops here and goes to 242,728. And that was just, so let's go all the way to the end, 224,758 trips just in October, but I only loaded in the October data. So that's quite impressive for 2016. It might have increased by then. So it's not so convenient to look at all the 242,000 data points. Often we're only interested in to look at the first 3 data points to see how the data looks like right now, for instance. So then I will often use this function .head, and you can provide a number here to only show the first, let's say, the first 3 rows in that data frame, which you get here. So one important thing when we talk about these data frames is that they have specific types. Each column has one and only one type. And Pandas tries to automatically detect which type is suitable for each column when you load in the data. And we can ask which type it used by using the .dtypes attribute, very similar to what we used from NumPy. So here we have start station is a integer of size, just an integer of 64-bit. Then we have start time is an object, which is a bit strange. These dates could be represented in a nicer way than just a general Python object. Then the end station is a floating point value, which is also a bit strange because we expected these to be integers. And then the end time is again an object, even though it should be a date. So clearly the automatic detection of these data types failed. Both start time and end time should be dates rather than objects, and the end station should potentially be an integer rather than a float. So we need to fix the types. The way we do that is that when we read the documentation about read CSV, there's a specific argument that we can tell Pandas which columns are dates, and that Pandas should try to parse these dates. So the problem is, right, that there's various different formats on how dates can be represented. And here we give Pandas a hint saying that both start time column and end time column are dates. Please try and parse them, try out various different parsing options to figure out which date format to use. So now I load it in again, and you see the star here, it means it's still working, and now the import takes a lot longer than before. So before I think it took a second, now it takes probably 10 seconds or so. And that's because Pandas needs to figure out how to parse these dates accurately. But now, if we ask for the dtypes again, we now see that indeed both start time and end time are now of type datetime of type datetime. And you can see also the formatting is slightly different. And so the reason why this is quite important is because often we want to, later on, maybe we're looking for only a specific range of dates, right? Maybe we're only looking for the data for one day, or maybe we want to compute averages for each day and so on and so forth. And these operations you can only do if the underlying data understands that this is actually time data, as a time series. So then the second problem that we had was that the end station was a floating point value rather than an integer. So the start station was integers, which makes sense because these are kind of the identifiers for the station where the trip started. But the end stations are, strangely enough, floating point values. So then one idea would be to say when we read in the CSV files, we can actually specifically say which type should be used. So I could say dtype end station np.n64. So I could specifically enforce it to use an integer. And so we can try that, and this fails. So it provides a value error, and if we go all the way to the bottom, we see that an integer column has not a number value. Okay? So we're trying to import something and map it into an integer, but it doesn't work because there's not a number value instead. And we can make this a bit more explicit. So here what I've done is I extracted the values of the end station and sorted them by their values, and then only printed the last ones. And so what you see is the end station indeed consists of some, here I only show the last 15 entries of the end stations, sorted. So the last trips ended at station 309, and then we have a bunch of trips that just never ended. And so these were trips where someone took out the bike and traveled around, but never put the bike back in again. Okay? And so then we don't have a value for that. And that's what's going on. So we can see that in October, right, there was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There were 11 trips where potentially maybe bike was stolen, right? Or maybe, maybe the person tried to put it in, but it didn't work for some reason. So, this would need to be investigated. But out of 242,000 trips, right, I don't think 11 kind of bikes or trips that didn't work out isn't so bad. And, maybe it could also be that maybe these are actually people who took the bike out on the 31st of October and decided to keep the bike overnight and put it in back on the 1st of November, which we don't see here. Right? So maybe the trip is still ongoing. Okay, so the next thing, now we've got all our data in a nice format. The next thing is that we want to select some part of the data that we're interested in. So the first thing that we can do is we can use this index notation to select a specific column. And you do that is you use the data frame name and then brackets and then the column name that you're interested in. So for instance, start station. And now you get a time series because you select a single column consisting of the indices and then the start stations. And so here I could say maybe I only want to see the beginning of it. You can also extract multiple columns at the same time. Then you need to use the double square bracket. And the result that you get is now not a time series but another data frame again, because you're having more than one column. So then you can also select rows. The notation here is a bit is very similar to the selecting columns, and so that can cause some trouble. But I show it to you anyway here. So you can use the square brackets and then numbers, integers, 5 to 15. And that selects the 5th to the 15th row. But in this case, the indices are the same here. So in fact, it looks like I'm selecting the index 5 to 14, but actually I'm selecting the row number 5 to 15. Right? So even this could be dates here, and I would still get the 5th row to the 15th row. So in general, though, if you're trying to select rows, or even more important, if you select rows and specific columns, it's better to use the .log attribute. So any data frame you can write .log, and then the notation is square bracket, the rows that you're interested in, and the columns that you're interested in. So in this case, for instance, if you're interested in row number, so here you actually provide the identifiers. So here I'm interested in the row that has the identifier 5 and the row that has the identifier 10. And for these ones, I'm looking for the column start time and end time. And so now you get a smaller data frame consisting only of 5, 10 and start time and end time. So you can also do the same. Oh, that actually doesn't work. Ah. No, there was definitely a way how to do that as well. Yeah, I need to look it up. Okay. So then, of course, it's very important that we are able to plot our data. And plotting data frames is very simple. So, well, specifically plotting series, a time series is very simple. But a series is very simple. So what I do is I extract a specific column, then I get a series out, then I restrict it to the top 100 data points, and I plot the results. So then what you get is, on the x-axis, you get the index of the data. So in this case, it was just integers from 0 to 100. And then the y-axis, you get the identifier of the start station plotted here as a linear plot. Of course, that's maybe not so meaningful here. But we can also plot multiple series at the same time. So if I want, here I extract both the start station and the end station and plot that. And then you get a plot that contains both the start station column and the end station column with different colors. Now, of course, here on the x-axis, it would be nice to actually have the dates rather than just these identifiers. So then what you can do is you can, in the plot function, you can provide a column that should represent the x data, or the values for the x-axis. So here what I'm doing is now I plot the first 20,000 trips, and I use as x-axis I use the start time, and what I'm plotting here is both the start station and the end station. And that's what it looks like. So there's an interesting pattern here, right? There seems to be a lot of trips going on here, and then suddenly there's a gap, and then the trips start again, and there's a gap. So we got an idea where these gaps might come from.
Rain.
Yeah?
Maybe rain. Rain.
Oh yeah, right. Yeah, that's a good point. So it might be rainy, so no one is cycling here. It might be quite extreme going from, I mean, there seems to be many, actually roughly 1,000 trips per day. And there seems to be very heavy rain if no one cycles. But it's a good...
You can't take the bike out between certain hours?
Right, so maybe you can't take out the bike between certain hours. So let's check the time here. So this is the 1st of October at 6 o'clock. What's this? 6 o'clock, the trips start. Then at 12 o'clock it seems very busy. At 6 o'clock in the evening it's still very, very busy. And then suddenly at midnight it's absolutely nothing until 6 o'clock in the morning. So probably what's happening is that between midnight and 6 o'clock in the morning you can't take out bikes. And if you look up the bicycles, you can actually see that that's the case. But this rain thing is really interesting, and I wonder, I mean, yeah, we would have to also use the data to figure out, but you know, probably you find some relationship between how many trips has been taken and how the weather is. That would be interesting. Okay, shall we stop here and start again at 1:15?